Everyone, my name is Carson Vikidam, and this is my Physics 2211 Lab 3 project titled Black Hole and Orbits. In this lab, I explored orbital motion using Newton's law of universal gravitation, first modeling a two-body system with a star orbiting a black hole, and then expanding it into a three-body system that includes a planet, moon, and spaceship. The main goal of this experiment was to study how gravitational forces influence orbital motion. Specifically, I wanted to see how objects behave when orbiting massive bodies, like a star around a black hole, and then how introducing a third object, such as a spaceship, affects the system's stability. Part 1 focused on calculating the mass of the black hole using the star's motion, and Part 2 added a dynamic spacecraft to test multi-body interactions. This simulation was built by Web v Python, aka glowscript, which allows for visual 3D modeling of forces in motion. The main objects are a planet at its center, the moon orbiting the planet in cyan, and a spaceship that launches from the moon in magenta. The system is governed by the universal law of gravitation, F equals g m1 m2 over radius squared, with the gravitational constant g. This equation is used in both parts of the lab to determine gravitational force between any two objects. In part 1, we modeled a star orbiting an unseen black hole. Using the velocity and position of the star, I calculated the change in momentum over time, which gave me the net force acting on the star. By rearranging the gravitational force equation, I could determine the mass of the black hole, MBH, equals force of gravity times r squared over the gravitational constant times the mass of the star. The constants in this equation were again the gravitational constant, the mass of the star, which was 2 times 10 to the 30th kilograms, and the change in time, which are at intervals of 1 second. From the simulation, the black hole's average calculated mass was approximately 1.82 times 10 to the 43rd kilograms, which is the average of all values calculated, and is consistent with supermassive black holes. Force vectors were visualized using colored arrows, orange for net force, magenta for parallel, and cyan for perpendicular components. These visualizations confirm that the star's acceleration always points towards the black hole. In part 2, we expanded the system by introducing a spaceship. The planet remained at the center, and the moon orbited it, and the ship launched from the moon's surface. Each object experienced gravitational forces from the others, so we used multiple force vectors to find the net force at each time step. In the code, I computed the gravitational force between all objects: planet on the moon, ship on the moon, planet on the ship, and moon on the ship. Then, using Newton's second law, F equals ma, I updated each object's velocity and position with the current velocity equals the initial velocity plus force net over m times change in t, and the um, current velocity or current position equaling the old position plus the updated velocity times change in time. The simulation stopped automatically if the ship collided with either the moon or the planet. The goal for this part was to give the ship a figure-8 trajectory between the moon and the planet. This required fine-tuning its initial velocity components, the ships, both x and y, so that it avoided crashing while remaining gravitationally bound. Through multiple test runs, I determined the ideal ship velocity range. In one run, a small increase in x velocity caused the ship to crash into the moon. In another, lowering y velocity led to an escape trajectory. Increasing y velocity. The most stable orbits balance gravitational attraction from both bodies. Key takeaways include, from this experiment, stable orbits depend heavily on the ratio of velocity to distance. Even slight changes in launch velocity produce drastically different outcomes. And the smaller mass of the ship makes it especially sensitive to nearby massive bodies. This demonstrates the chaotic nature of multi-body gravitational systems. Possible errors included numerical integration drift from the finite changing time and simplifying the simulation between two dimensions. Relativistic effects were ignored, but these would be significant near massive bodies like black holes in the real life. To minimize error, smaller time steps and repeated tests were used, though they could be used heavier or more heavily in the future. In conclusion, this lab successfully modeled gravitational orbits for both two-body and three-body systems. We verified that orbital stability requires precise balance between velocity and gravitational force. The main takeaway? Even simple models can reveal the complex and sensitive dependence of orbital mechanics on initial conditions. Thank you.